everyone, I'm going to go ahead and finish up section 4.4 with the remaining examples. These ones, some of them anyway, are a little bit tougher, and I also had to take a break to answer emails. I don't know if you could hear them, but they were popping in really quickly, and I've been trying to keep up with that so I don't get hundreds in my inbox again. Okay, so let's work through these last example. Example number 5 is the limit as x goes to infinity of ln x all squared over x. Okay, so if we take our first move and we try to run this limit through, we could see, or we should see, that we'd get infinity over infinity, which is not very helpful. And that means that we need to try to use algebra, which you could probably also see there's no simplifying we can do here. That is also not helpful. And that tells us we're going to use L'Hopital's rule. All right, so I'm going to denote that I'm using L'Hopital's rule. Rewrite my limit. All right, I'm going to take the derivative of the top. So notice we need the chain rule for the top. The derivative of the outside being 2 ln x, the derivative of the inside being 1 over x, right? And now taking the derivative of the denominator, I would just get 1, right? So rewriting this, not using L'Hopital's, just rewriting. This is the same as 2 ln x over x. That's because I don't need to rewrite this 1, and notice if I multiply 2 ln x by 1 over x, I get 2 ln x over x. Okay, so now let's try to run our limit. Notice if I try to run this again, I still get infinity over infinity, and I have a fraction, which means I can use L'Hopital's again. When I do so, I'd have the limit as x goes to infinity of 2 times 1 over x divided by 1. Rewrite this so it's a little bit more nice looking. Okay, the numerator is the same thing as 2 over x after I multiply, and it's not necessary to write that I'm dividing by 1. So at this point, I can clearly see what's going on. If I have x going to infinity, I'm dividing a constant by a very large number, which hopefully recall tells us this is going to 0. So my limit here is 0. Okay, example 6 is even more tricky. So with this one, again, we'll try to run that limit first. If we run the 0 through, what we would have on top, okay, if you think about this, if we have x to the x, all right, you can see the x is approaching 0 but never actually hits it. The x and the exponent is doing the same thing. So this entire thing would go to about 1. So I'll type that out. The numerator, probably don't want to use green if I'm typing this much. It's a little hard to see. Okay, the numerator goes to 1 since the exponent is going to 0. Okay, and we know the base, I guess you could say, is some constant approaching 0, but it doesn't hit it, so yes. Okay, so anything to the 0 power is 1, that would be going to 1, and then you're subtracting 1, so the numerator goes to 0. Okay, subtracting 1. So numerator goes to 0. All right, let's see the denominator here. Okay, if we take the limit as x goes to 0 from the right of the natural log of x, you'd have to sketch that natural log function out to see it. So if you need to, just draw that function out real quick and see what happens. But if you do that, then you would end up getting, let's see, that entire thing going to negative infinity, essentially. Okay, so note that, I'll write that out. So the natural log of x goes to negative infinity as x goes to 0 from the right. Right, so if you need to, you might want to look at the natural log function to figure out, you know, how that looks exactly. All right, and now if you think about the plus x part, that'll go to 0 or approximately 0, and negative 1 is a constant, so we know that negative infinity is dominant in the denominator. So negative infinity is dominant in the denominator. All right, so now thinking through this, if we're like, oh, okay, well, I get 0 over something that's going to negative infinity, if you look at the function, there's no way to manipulate that algebraically. When we have x to the x power, we've always had an equivalent statement, so we can use logarithmic differentiation on that. That's not an option. However, we should recall from previous sections that we can use intuitive reasoning to figure out what's going on. So here we see the numerator is going to 0. The denominator is going to negative infinity. Okay, so we're dividing a small number by something really big, which means this is going to go to 0. So dividing a small number by a large value, okay, the whole thing will go to 0. All right, so that one's a little bit more tricky because you can't really use L'Hopital's when you have that x to the x power, at least not without an equivalent statement there. That means we need to resort to that intuitive reasoning that we talked about at the beginning of the course. Okay, so number 7 is again tricky, but in a different way. So on this one, we have the limit as x goes to negative infinity of x times the natural log of 1 minus 1 over x. All right, so this, notice it's not even in fraction form. So as it's written right now, we can't use L'Hopital's rule. If we run the negative infinity through, we get something that's an indeterminate form, meaning we don't really know what's going on because we'd have like a negative infinity times something, which doesn't tell us a lot. So what we're gonna have to do is first get this in fraction form so we can use L'Hopital's rule, and then we'll have to use L'Hopital's rule. So this is equivalent to, oops, back to the pen here. All right, this is equivalent to the limit as x goes to negative infinity of ln of 1 minus 1 over x, all divided by 1 over x. All right, so algebraically, mathematically, if I divide by 1 over x, remember that's the same as flipping and multiplying, so it's really the same as multiplying by the x. So I just change the way I've written the x essentially. It still means the exact same thing. All right, so now I do have a fraction, and I'm also in indeterminate form, which means that I can go ahead and apply L'Hopital's rule. So the first step, I'm just rewriting to allow myself to use L'Hopital's rule, and now I'll actually use it. So I have the limit as x goes to negative infinity of, I need to use the chain rule in the numerator. When I do so, I have 1 over 1 minus 1 over x. Okay, now I need to multiply by the derivative of the inside. Okay, so here I have to notice this is the same thing is negative x to the negative 1 with that minus sign right there. So the derivative of 1 is 0, but the derivative of negative x to the negative 1 would give me, it's times a positive x to the negative 2. Right? And then this entire thing is divided by, again, this is just x to the negative 1 this time, so negative x to the negative 2. Right, so notice here, algebraically, not using L'Hopital's, doing a little bit of algebra, a little bit of arithmetic here. Okay, so this is the same as the limit as x goes to negative infinity. Right, these divide out to 1, so we're left with negative from this negative in the denominator, 1 over 1 minus 1 over x. Okay, at this point, we try to run this limit, right? We know the top will just go to 1, right? The bottom, this part is going to go to 1, and we should see that 1 over x is going to go to 0 if we divide it by that large negative. So what we end up with is, I'll just write this, equals negative 1 over 1, which is just negative 1 for our final answer. All right, so this one's kind of tricky, but the key thing here, the key trick here is to make sure you have that denominator, which is going to allow you to use the L'Hopital's rule. All right, let's move down, and I believe, yep, this will be our last example. All right, so looking at our last example, we have the limit as x goes to 0 of the cosecant of x minus the cotangent of x. All right, so to know what's going on here, you'd have to remember what those cosecant and cotangent graphs look like. If you just look those up real quick, you'll see that as x goes to 0, you have asymptotes for both of them, and so they're approaching either infinity or negative infinity, which means this is definitely an indeterminate form. All right, there's, I think pretty clearly, not a lot of algebra we can do to change this so we can work with it nicely. And that means that we want to make this so we can use L'Hopital's. Well, in order to use L'Hopital's, it should be an indeterminate form, or it can be, and you need to turn this into a fraction. So I'm going to have to use a little bit of algebra, or trig, to turn this into a fraction first. So I have the limit as x goes to 0 of cosecant is the same thing as 1 over the cosine, sorry, I'm just getting the sine, 1 over the sine of x minus cotangent is the same thing as cosine over x over sine of x. Okay, so this works out kind of nicely because we have a common denominator here. So this is going to be the same thing as the limit as x goes to 0 of 1 minus the cosine of x over the sine of x. All right, so now I have this in fraction form, which is good. Let's see if running the limit gets us anywhere, but I don't think it will. So if you run 0 through cosine, you end up getting a 1. You'd get 1 minus 1, which is 0 on top. If you run it through sine, you get a 0. So this is still an indeterminate form, which means that we need to go through and use L'Hopital's rule. So using L'Hopital's rule on this, we have the limit as x goes to 0 of, take the derivative on top, so the derivative of 1 is 0, the derivative of negative cosine is, the derivative of cosine is negative sine, so you'd have a negative times a negative, which turns into a positive sign. The derivative of sine is positive cosine. All right, at this point, let's check to see if we can actually go through and run our limit. So if we take the limit as x goes to 0 of sine, we'd get a 0 on top. And the limit as x goes to 0 with cosine, so running it through cosine, we'd get a 1 on bottom, which leaves us with the defined valid answer of 0, and that would be our final answer. All right, so main concept here is if you have something that's a fraction in your indeterminate form, or if you can turn something into a fraction and then you're in indeterminate form, you can use L'Hopital's rule to find the derivative, and you can use it multiple times in one question. The homework will be pretty similar to this. It will require a little bit of other algebra, maybe be slightly harder, but again, we want to give ourselves the chance to kind of think through that tougher stuff with this little root that we have. So make sure that you follow up with questions on the discussion boards if you happen to have them. Thank you.